we're going to go ahead and look into example 7.1. It states how much work is done on the lawnmower by the person in this figure, which is this one here. Okay, so how much work is done by the person if he exerts a constant force of 75 newtons at an angle of 35 degrees below the horizontal and pushes the lawnmower 25 meters on level ground. Okay, so what we will do is we remember that work is the force, okay, the magnitude of the force times the magnitude of the distance, the total distance, times cosine of the angle between the two. Okay? Or displacement. I'm sorry, not distance. Displacement. Okay, so this is going to be the constant force, which is 75 newtons. Okay? Times dr, which is the displacement, 25 meters, times cosine of 35 degrees. Okay? Give me just a second. I need to grab my calculator. Alright, so the work done will be 75 times 25 times cosine of 35 degrees. That will be 1,500 and we'll say about 40. And this is in Newton meters. Or it will be, should be a comma, in joules. Okay, so this is the work done by that person pushing the lawnmower. Okay? Alright, so let's now look at work done by friction, which is a contact force. So we have two objects sliding on a surface. Okay, there is some kinetic friction, and it is opposite to the displacement. Okay, so we looked at friction a little bit. So if we have a book, okay, sliding across a table, say in this direction, this is where it's heading. Okay, we have some frictional force on this surface, okay, opposing that movement. Okay, so this is what we're looking at. Okay, so basically what this means is that work done by kinetic friction will be negative. Okay, so if the magnitude of a frictional force is constant, the work done by the friction is as so. So we have our work done from A to B is equal to our integral of our force dotted into our displacement. Okay, so we can say that is going to be negative F sub k times the integral here from A to B times the magnitude of dr, okay, or the displacement here. Okay, and then when you take your integral here, you get the magnitude of L from A to B, which is going to be your path length on that surface. So if we have our book that moved, I don't know, say 2 meters, okay, that is what you would plug in here. So this would be our displacement, but it is going to be the length. Okay, so maybe displacement isn't the best. Well, yeah, displacement makes sense. You want to say it's from A to B, okay? No matter what that path is, okay? So let's go ahead and put this onto an example, okay? We are looking at example 7.2. It states you decide to move your couch to a new position on your horizontal living room floor. The normal force on the couch is 1 kilonewtons, okay? And the coefficient of friction is 0.6. part A states you first push the couch 3 meters parallel to the wall and then 1 meter perpendicular to the wall. Okay, so from A to B. So we make this path. Okay. We want to know how much work is done by the frictional force. Okay, so again, our work done from A to B is minus F sub k times the length from A to B. Okay, so the length of this path. So one thing to note, F sub k is going to be equal to our normal force, okay, times our coefficient of friction, mu sub k, okay? So we want to make sure that we keep that in mind when we're plugging all of this in, okay? So our work is going to be negative, our normal force, or we can put our coefficient of friction first. You should probably do that. Mu sub k times n. I believe that's how your book has it. Doesn't matter, you're multiplying. All right. So we'll say our coefficient of friction, 0.6, times our normal force, which is 1 kilonewton. Okay. So remember, kilo, or K, is going to mean it's 1,000 times whatever it is, right? So this is 1,000 newtons, okay? And then we have times this length. So our total length is going to be 3 meters plus 1 meter. Okay, that's the total length of the displacement here. Okay, so we have 0.6 times 1,000 times 4. So our work done is 2,400 Newton meters, or 2,400 joules. Okay? So this is our work done from A to B. Okay, now part B says we don't like the new position, so we move it straight back to its original position from B to A. We want to know what the total work done against friction, moving the couch away from its original position and back again. So we're not just looking from B to A, we are looking from A to B and from B to A. Okay, so I'm going to say work tot is going to then be, okay, it's going to be, let's see, against friction. So it'll actually be, since it's against friction, it's going to be the positive. Okay, so we're going to say it's positive F sub k, which is 0.6 times 1 kilonewton times our displacement, which is 3 meters plus 1 meter plus our total length of our path. This path length is unknown, right? So we'll have to use the fact that these make a right angle, and we'll use trigonometry. Okay, so this will be C, I'll call it, and it'll be the square root of 3 squared plus 1 squared. Okay, so 3 squared is 9 plus 1 is 10, so it'll be the square root of 10, and again in meters. So now this will be, let's see, whoops, putting it into my calculator, 4 plus the square root of 10. Okay, so putting this into my calculator, I get 4,000 and I'm going to say 300, okay, joules. So again, it could be Newton meters, but I'm going to just go ahead and say it's joules. And so that is going to be your total work done here against the friction. All right, so note a couple things when I'm looking at the language that the problem chose. If we're saying that we want to know the work done by the frictional force, we make sure we have that negative here, okay, in this formula. Now, when it says against friction, we're going to have a positive value, okay. One other thing to note is that kilo, okay, the kilonewtons, we could have left this in kilojoules. That's another thing you may see. So this would also be negative 2.4 kilojoules, okay? And this one here, the total work done could be 4.3 kilojoules. Okay, so just watch out for that when you're going through looking at the textbook as well as doing your homework. All right, so let's go ahead and move on to another contact force, and that is going to be gravitational force. Okay, so the idea is that near the Earth's surface, we have a gravitational force on an object of some mass m, and the gravitational force has a constant magnitude. Okay, again, that's near Earth's surface. When we get further away from Earth's surface, things change a little bit. That gravitational force will change. Okay, but for now, looking at near Earth's surface, we're saying that the gravitational force, this has a constant magnitude, and that will be m times g. Okay, and it has a constant direction, which is going to be vertically down, and typically we say that it's in the y-axis. Okay, so typically we say that this is our coordinate system, okay, or even ignoring this one, usually this is y, okay? And if our Earth's surface is so, then y would be in that vertical direction, okay? All right, so work done by gravity is going to be equal to the weight, or mg, times the displacement, okay? So again, let's go ahead and define our gravitational force in the y-axis in Cartesian coordinate systems. So we have F gravity is equal to negative mg j hat. Okay, j hat again is in the y direction. Okay. And so the work done by gravity over any path from A to B is going to be this. Okay, it'll be negative mg j hat, which is our F grav. Okay. And this is from before when we were looking at our paths over some constant force. Okay. So this would be our r, okay, our displacement. And when we take that and we apply the dot product, we obtain this, negative mg times y at b minus y at a. Okay, so this is our work done by gravity over some path. Okay, so let's go ahead and go on and look at work done by forces that vary. And the best way to do this, I think, is to look at an example. Okay, so we're going to go ahead and look at example 7.4, where we have some object that's moving along a parabolic path, and we have that path described here. From the origin to some point 2, 2, okay, under an action force, F bar is equal to this here, okay, and we want to calculate the work done. So we'll go ahead and do this in the next video.